So, hello everyone at the Cosmology from Home 2022. I am Gonzalo Morrás and I'm going to present you some work that I have been doing together with Juan García Bellido and Sabas Neseris on a search for gravitational waves from black hole hyperbolic encounters in LIGO-Virgo. So the main motivation to do this search is that there are some models that predict dense black hole clusters in our universe, such as primordial black hole models or models for the centers of galaxies and globular clusters. Black holes in these dense environments will scatter off each other in hyperbolic orbits, which will look something similar to the sketch that I show here below. Whenever these hyperbolic encounters are sufficiently close, that is when their periastron distance is sufficiently small, they will emit a large amount of gravitational waves that will be detectable by current interferometers on Earth, such as LIGO and Virgo. However, before this work, no targeted search for close hyperbolic encounters had been carried in gravitational wave detectors. To actually do this search, we will first need some ingredients, starting from theoretical templates of the gravitational waves emitted by the close hyperbolic encounters. We will also have to characterize the signal that these gravitational waves from close hyperbolic encounters leave in lasing interferometers, and using the properties of this signal and of the noise of the interferometers, we will have to determine the data processing techniques to make the close hyperbolic encounter signal stand out over the detector noise. Finally, to do the search, we will develop a trigger to select the data that might contain a close hyperbolic encounter and distinguish it from noise, and our trigger will consist on two steps. The first step will make a data preselection based on correlations between the different interferometers, and the second step will utilize a convolutional neural network to determine which correlations can come from a close hyperbolic encounter and which will come from noise. But let's start talking about the templates. So the problem that we want to solve is we will want to determine the scattering of two gravitational interacting masses M1 and M2 with spins S1 and S2. And we will want to find the gravitational radiation emitted by this system. However, no analytical solution to this problem exists in general relativity. And numerically solving instance equations many times will be computationally cost prohibitive. Because of this, we will have to do an approximation. In our case, we can use the post-Newtonian approximation because in a close hyperbolic encounters, black holes do not get very close, not as close as in the compact binary coalescence case, where there is a merger and a breakdown. And also, since close hyperbolic encounters only pass through periastron once, and we are going to use machine learning methods to find these events, accurately following the phase for many cycles will not be as critical. We will only want to capture the main phenomenology. Because of this, we will use the post-Newtonian approximation, taking only up to leading order spin effects, which are of order 1 over the speed of light to the cube or order 1.5 post-Newtonian. So I will not bore you with the details of how these post-Newtonian equations are solved, which are quite cumbersome and not very enlightening. You can check the details in the paper if you are interested. By the typical gravitational wave that are emitted by these close hyperbolic encounters are similar to the ones shown in figure 2, where you can observe that the gravitational waves perform only one oscillation. This is quite easy to understand if we remind ourselves that gravitational waves are quadrupolar in nature, and because of this, their frequency is peaked at twice the orbital frequency, and since close hyperbolic encounters only perform half of an orbit due to the fact that they have a periastron but they do not have an aphastron, gravitational waves from close hyperbolic encounters will perform more or less one oscillation. Okay, so to actually find the signal that these gravitational waves leave in a laser interferometer, we will have to project them into the detector by using the antenna patterns. And since we want to find them at 3 different detectors at the same time, we have to take into account the light travel time between detectors. That is the time that the gravitational waves takes to go from one interferometer to the other at the speed of light. So here I show you the signal in the 3 interferometers that we're going to be interested in, Livingston, Hanford, and Virgo. And what you can observe is that if you know about gravitational wave data analysis, is that these close hyperbolic encounters look quite similar to some very common transient source of noise, which are blip glitches, whose origin is a bit unknown. But it will be quite a difficult problem that these gravitational waves will look similar to some common noise artifacts in gravitational wave detectors, and this is something that we will have to fight with. Okay, so now that we have characterized the signal, we will have to determine the data processing techniques to make it stand out over the large amount of detector noise that there is in actual real interferometers. So the first thing that we have to take into account is that below 20 Hertz, there is a large increase in seismic and thermal noise in the detector, and we will not be able to measure anything below this 20 Hertz mark. And also of 800 Hertz, there will be a very small amount of close hyperbolic encounter signal, since these close hyperbolic encounters tend to be very low frequency events. Because of this, we will have to remove the noise-dominated frequencies applying a 20 to 800 Hz bandpass. However, even in the frequencies that remain in this 20 to 800 range, not all frequencies will have the same noise, since the noise in gravitational wave interferometers is colored. To fight with this, we will widen the strain, which means to weigh down the strain in the noisiest regions to make all the frequencies have the same noise. The next thing that we will have to take into account is that since gravitational waves from close hyperbolic encounters only perform one oscillation, due to the Fourier uncertainty principle, they will have an extended time frequency structure. So we'll want to represent these gravitational waves in the time frequency domain, which we will do by using the Q transform. So here I show you an example of how it looks when you inject an example close hyperbolic encounter in the detector output, which in the context of gravitational waves only means adding the gravitational wave signal to the actual experimental strain, and we filter, whiten, and Q-transform the data containing this injection. So the first thing that we realize is that the shape of the signal is more or less like a teardrop, with most of the signal at low frequencies, and we see that we observe the signal the strongest in Livingston, because this is the most sensitive interferometer, especially at the low frequencies at which close hyperbolic encounters are. This interferometer is followed in sensitivity by Hanford and then Virgo. Okay, so now I will start talking about the actual search for close hyperbolic encounters that we are going to do in LIGO-Virgo. So again, the first thing that we have to take into account is that these close hyperbolic encounters look very similar to some common blip glitches, which will be some transient sources of noise. To be able to reject these blip glitches, we'll have to use coincidences between detectors, because the noise will be uncorrelated between the detectors, since these detectors are hundreds of kilometers apart, but gravitational waves will leave a signal that is coincident between the different detectors, since it travels at the speed of light. To do this rejection using coincidences, the more detectors online we have, the better we can, the more we can improve the search sensitivity. Because of this, we will analyze the public LIGO-Virgo O2 data with all three detectors in nominal operation, which corresponds to 15.3 days of data. Since close hyperbolic encounters only do one oscillation, burst methods, which are methods to look for gravitational waves using unmodeled searches, are competitive with and can even outperform match filtering techniques to do the search. In our particular case, we will use a two-step trigger to look for these close hyperbolic encounters. The first step utilizing a correlation trigger, and the second step utilizing a convolutional neural network. But let's start talking about the correlation trigger. So the main idea is that we want to make a loose trigger to preselect those events that can contain a gravitational wave for the neural network to then analyze. Given the fact that the better the data that we fit and use for the neural network, the better the results we can expect to obtain. Because of this, we will look for correlations in the time frequency domain with Pearson's coefficient, which is defined as here. And for the actual trigger discriminant, what we will do is we will choose a linear combination of the correlation between Livingston and Hanford and the correlation between Livingston and Virgo. In O2, doing some injections of close hyperbolic encounter signals, we determine that the optimum value of this A parameter in the linear combination is around 2/3. That is, giving a higher weight to the correlation between Livingston and Hanford, which makes sense since these two are the most sensitive interferometers. In our case, to then fit to the neural network, we will preselect the images that have a trigger discriminant greater than 0.3. Okay, so the first thing that comes to mind once we have defined this trigger is what fraction of close hyperbolic encounters can we detect as a function of their loudness, which in the context of gravitational waves, we measure by the signal-to-noise ratio. To answer this question, what we do is we inject close hyperbolic encounters with random parameters and run the correlation trigger over them. What we observe is that the larger the signal-to-noise ratio, that is, the louder an event is, the more likely are we to recover it. Which makes sense given the fact that they will be easier to spot. And what we also observe is that we are accepting most events with a signal-to-noise ratio greater than 10. Okay, so the next thing that we ask ourselves is whenever we run this trigger over the data, how many events are we expected to generate coming only from noise? To answer this question, what we do is we estimate the number of expected noise events by running the trigger on shifted data. So what shifted data means is that we take the timeline of Hanford and the timeline of Virgo, and we shift it in time a couple of seconds in such a way that correlations between the different interferometers become non-physical. What we obtain is by doing this is the number of expected noise events, which is shown here with the gray lines. And what we observe for this is that the larger the trigger discriminant is, the less number of events we expect to come from noise, which makes sense given the fact that we are discriminating noise against signal. Okay, so we also have shown here with the dots the actual number of events that we obtain whenever we run this trigger on the data without doing any shifts, which we observe to be consistent with the number of expected events. Okay, so putting the actual trigger discriminant threshold at 0.3, we preselect 2,704 images. So what we will want to do now is we will want to classify which of the 2,704 preselected images come from noise and which come from close hyperbolic encounters. For this, we will use a neural network, which is a mathematical model to analyze data using machine learning. And it is sketched here. So the input of the neural network will be the pixels of the image we want to classify, and the output will give us will be a number between 0 and 1 that will give us the probability of the image to be a close hyperbolic encounter. Between the input and the output, we will have the hidden layers, which are used for internal calculations only, and they contain free parameters which will be fed to some training data. In our case, we use one of the most refined architectures for image classifications, which are residual convolutional neural networks. Okay, but to train and actually use the neural network, we'll have to have some images. And here I'm going to show you how we define the images. So what we do is we put the normalized energy of the three detectors in the same image. So here in the top is Livingston, then Hanford, and then Virgo. And for the duration of the images, we pick 0.7 seconds so that the neural network has a bit of information of how the data looks around the event. So we have three different classes of images. We have close hyperbolic encounter images, which are obtained by injecting close hyperbolic encounters into shifted detector data and finding and selecting those that are detected by the correlation trigger. Then we have the noise images, which are just the ones that we obtain when we run the correlation trigger on shifted data. And obviously, the shifts in the close hyperbolic encounter images and the noise images are different. And finally, we have the data images, which are the ones generated by the correlation trigger when no shifts are applied to the data. Okay, so using these different sets of images, what we do is we train the neural network with the close hyperbolic encounter images and the noise images, which training the neural network means finding the internal parameters such that whenever we input a close hyperbolic encounter image, the network returns a 1, and whenever we input a noise image, it returns a 0. Because of this, we say that the neural network output can be interpreted as a close hyperbolic encounter probability. In our case, we trained the neural network on 64,000 noise images and 45,000 close hyperbolic encounter images. And we will consider an image a close hyperbolic encounter if its probability of close hyperbolic encounter, that is, if the output of the neural network is greater than 0.9. So again, having put this threshold, we ask ourselves how many events, how many close hyperbolic encounters do we recover as a function of their signal-to-noise ratio, which is what is plotted in this figure. So again, we can observe that the larger the signal-to-noise ratio, the larger the fraction of events that we recover, which makes sense given the fact that louder events will be easier for the neural network to spot. And we are able to detect most of the close hyperbolic encounters with signal-to-noise ratios above 5. So the next thing that we ask ourselves is what will be the distribution of the data with the close hyperbolic encounter probability. And we want to compare this with the expected distribution if only noise was present, which again, we obtain by running this neural network on the shifted images. So the expected distribution is given here in orange, where you can observe that the larger the close hyperbolic encounter probability, the less likely it is so the less number of events we obtain, which makes sense since this should all be noise. And we observe that the observed number of events follows quite closely the expected number of events. It is a bit higher, it's a bit over the expected number at large close hyperbolic encounter probabilities, but it's consistent between the two of them. In the last bin, at a probability of close hyperbolic encounter greater than 0.9, we expected to find 7.5 plus or minus 2.7 noise events, and we observed 8. That is, the number of events that we observe is consistent with the number of expected events coming only from noise. So we can say that we cannot claim any detection. Okay, so now I'm going to talk about the most significant events that are discovered, that are found by this neural network, and I show the two most significant in this slide. So you can observe that they look quite similar to compact binary coalescences with a chirp-like signal, and that is because they are. So the two most significant events recovered by the neural network correspond to GW17014 and GW17009. This makes sense because the neural network has been learning how a gravitational wave signal looks, but it has not learned too good to discriminate between close hyperbolic encounters and compact binary coalescence, especially because the final stages of the compact binary coalescence can look sort of similar to a close hyperbolic encounter. Okay, so we do not claim that these are close hyperbolic encounters. There are compact binary coalescences that have been cataloged by the LIGO-Virgo collaboration. Okay, so now moving on to the next most significant events, we have these two, which are not cataloged by any of the searches for compact binary coalescence, and they could in principle be close hyperbolic encounters, although they are not very likely to be due to the fact that the number that we observe is consistent with the expected number. But in any case, one could study whether or not they are by doing Bayesian inference or stuff like that, and this is left as future work. Okay, so just to conclude, we have in this work, we have determined the gravitational waves emitted by close hyperbolic encounters and characterized how they look in real gravitational wave detectors. We have looked for close hyperbolic encounters in LIGO-Virgo data using burst methods and machine learning, and we have found 2 of the 3 binary black hole mergers contained in the data analyzed. We will then have obtained 6 further candidate close hyperbolic encounters on which one could perform further analysis, and the number of events is consistent with noise, so we cannot claim any detection. So I will be happy to hear all your questions and everything in the discussion sessions.